Graphs of logarithmic functions, example 1. So we have to consider the function f y equals logarithm in base 2 of x minus 1 plus 1 and find the domain and range of this function. So let me copy it first. So it's the function f y equals logarithm in base 2 of x minus 1 plus 1. Now if you compare this to the general family of functions described in the video assigned for today, you see that it should correspond to this: k times logarithm in base a of x minus m plus n. And if you compare k to this number here, which is 1, if you compare m, you can compare it to this number 1, and finally when you compare n to this one, you can conclude that k is 1, m is 1, and n is 1. So this function here has to do with the original function f sub 0 y equals logarithm in base 2 of x, which is multiplied by 1, so I don't have to write this number 1 in front. So the graph of this function that we are going to study in this example is going to be related to this simple logarithmic function, and the relationship is very simple. The one that we are trying to describe is translated, well, is the result of the translation of the original graph by one or through one unit in the horizontal direction and through one unit in the vertical positive direction. Okay, so now let us start with part A. Find the domain and range of f. So the domain of f, the domain is the set of all numbers for which it is defined. Now look, if you see the formula for the function, there is the logarithm of something. This number in the brackets has to be such so that the logarithm can be calculated. So we already know that x minus 1 has to be positive because we can calculate logarithm only from positive numbers, and it has the consequence that if you now add 1 to both sides, you get x is greater than 1. So the domain of the function consists of all real values x such that x is greater than 1. Okay, so this is the domain. As for the range, well, you remember that the original function, the logarithm in base 2 of x, has the range equal to the set of all real numbers. So the range consists of all real numbers. And if you shift this function in the horizontal direction and then in vertical direction, it doesn't have any effect on its range. It still will have the range of the range equal to the set of all real numbers. Therefore, I can say that the range of this function f is the set of all real numbers, like that. Now, in part B, we are asked to find asymptotes and axis intercepts. So, as for the asymptotes, now you know that this simple logarithmic function had the asymptote x equals to 0. So it approached this axis and never touched it, never crossed it. It was the vertical y-axis. This was the asymptote. And if you shift this function by 1 unit to the right and by 1 unit upwards, this asymptote will change to x equals 1. So x equals 1 is the vertical asymptote. Okay, like this. So it has to have this asymptote. As for the intercepts, you may imagine that this function is going to intercept either the x or the y-axis. So let us first try to think about the x-axis intercept. okay, intercepts. So these are the points for which y equals 0. So let me substitute 0 for y into the expression of the into the formula of the function. So the formula was y equals logarithm in base 2 and so on and so on. So I substitute 0 for y and I get logarithm in base 2 of x minus 1 and all that plus 1. Okay, so now I want to find the corresponding value of x, which corresponds to this intercept, x-axis intercept. So I subtract 1, so I get minus 1 equals logarithm in base 2 of x minus 1, and now I can express the logarithm minus 1 as the logarithm in base 2 of 2 to the minus first power equals the logarithm in base 2 of x minus 1. Now I can compare these and get that minus 1 equals x minus 1, I can get that 2 to the power of minus 1 on this left hand side. Let me correct this. It's 2 to the power of minus 1 equals x minus 1. So 2 to the power of minus 1 is 1/2, which should be equal to x minus 1, and hence if you add 1 to both sides you get x equals 1 plus 1/2, which is 3/2. So the x-axis intercept is 3/2 or 1.5 exactly. So this should be the x-axis intercept. As for the y-axis intercept, the y-axis intercept, I can write it here, y-axis intercept. Any such intercept would have its x-coordinate equal to 0. But you see, since x has to be greater than 1, it can never be 0, and therefore we can conclude safely that there are no y-axis intercepts for this function, because all the points of its graph have the x-coordinate greater than 1. So this is okay. It's part B. We have found only the x-axis intercept, which is 1.5. Now in part C we are asked to sketch the graph of f showing all important features. So I have prepared the set of axes. So this one is the x and this one is the y-axis, and also a pair of dashed lines which correspond to the shift, to the translation. So let me use black color to represent the graph of the original function. So the original function f sub 0 is the function logarithm in base, here it was the logarithm in base 2 of x, logarithm in base 2 of x. So this function has to pass through this point with coordinates 0 and 1, okay, and it also has to pass through the point with coordinates 2 and 1, okay, because the logarithm in base 2 of 2 is 1 and logarithm in base 2 of 1 is 0. So the graph of this function would behave perhaps like this. So it has the y-axis as its vertical asymptote, which it approaches but never reaches, and it is perhaps in this form. So this would be the logarithm in base 2 of x. Now we need to draw or sketch the graph of the function f, which is the function y equals logarithm in base 2 of x minus 1 plus 1. So this function we already know is obtained by translating the original function by 1 unit to the right and 1 unit upwards. So this point here gets translated to 1 unit to the right and 1 unit upwards, so it gets here. and the original point which is below it is translated by 1 unit to the right and 1 unit upwards, which is here. And it means that the new graph should pass through these 2 points like that, and should have this behavior, should approach this line, because this line is the shifted y-axis, which is shifted by 1 unit to the right and 1 unit upwards, and this should be its vertical asymptote. So this line which has the equation x equals 1 is the vertical asymptote of this function. So this function here is the logarithm in base 2 of x minus 1 plus 1, like this. So you see it's strictly increasing. Its domain is really the domain really consists of all numbers which are greater than 1. I forgot to include numbers here, so this is 1, 2, 3, 4 and so on, and this is 1, 2, 3 and so on. So minus 1 perhaps, and so you see its range, its domain is consists of numbers which are greater than 1, and the range of this red function is represented by all real numbers. Okay, now there is the last part, part D, in which we are asked to find f inverse and explain how to verify our answer. So let us start with the original function. So the original function here is y equals logarithm in base 2 of x minus 1 plus 1. To obtain the inverse, we know that what we have to do, we have to interchange x and y. So instead of y, I write x equals logarithm in base 2 of y minus 1 plus 1. And now I want to express y, since this should be the formula expressing the value of this function. So subtract 1 from both sides, so you get x minus 1 equals logarithm in base 2 of y minus 1. Now x minus 1 can be expressed as logarithm in base 2 of 2 to the power of x minus 1, like that. And this should be equal to the logarithm in base 2 of y minus 1. Now, since the logarithm is one-to-one function, you can conclude that 2 to the power of x minus 1 is y minus 1. And now you can add 1 to both sides and get the formula y equals 2 to the power of x minus 1, and this should be plus 1, like this. So this function here is the inverse to our logarithmic function f. You see it's the exponential function, and this function is also related to the simple exponential function 2 to the power of x, and is obtained by translating it by 1 unit to the right and 1 unit upwards, like that. Now if you want to verify our answer, there are 2 ways how to do it. One has to do with the graphs. So let me go to GeoGebra and type in the formula for the original function. It was y equals logarithm in base 2 of x minus 1 plus 1. So you see the GeoGebra has the special function in which, logarithmic function in which the base is part of it. You write it here. So this is our function f. You see the result corresponds to the sketch that we obtained just by using our knowledge about translations and so on. Now, if I want to show the inverse, I have to write another formula, and it should be 2 to the power of like this, 2 to the power of x minus 1 and all plus 1. Okay, and the third thing that I include is y equals x, which is the diagonal of the first and third quadrant. Now you can see yourself that this original function of ours the logarithmic function, its inverse, they are related, and they are related in such a way that they are each other's reflection in this line. So this is one way how to do it. It's a graphical way. Another way how to obtain or how to verify our answer is to use the typical thing that we do when we want to show that the function is the inverse of the other function, and it is namely to show that f of f inverse of x is identical to x. So let me do it. So it should be the logarithm in base 2 of, now instead of x I should have the inverse 2 to the power of x minus 1 plus 1, then minus 1, and all plus 1. And I should be able to show that this is equal to x. So is it? I don't know. Let me see. Well, it is, because these two numbers cancel each other out. And now I have the logarithm in base 2 of 2 to the power of x minus 1, which is x minus 1. And I have to add 1 here. And you see that this really is x. Okay. Also, what should be true is the following. F inverse of f of x should also be identical to x. So f inverse is 2 to the power of, so this function here, and instead of x I will write logarithm in base 2 of x minus 1 plus 1. Now I have to take away 1 and add 1, and I ask, is it equal to x? Well, let us see. These two numbers cancel each other out, and now I have 2 to the power of logarithm in base 2 of x minus 1. So you see this first exponential is just x minus 1 plus this 1, it's really equal to x. So x equals to x. So this proves actually that this function is the inverse of this original function. Now there is one thing that I forgot to include into my graph, and it's this number here. And this number is the horizontal axis intercept, which should be 1.5, because this is what we calculated here. So sorry for it, I forgot. Here it is. You see that the x-intercept is here, and the red function has no y-intercepts at all.